This scientific paper titled, Thermo-Responsive Ultrafiltration Block Copolymer Membranes based on Polystyrene-block-Poly, diethyl acrylamide, focuses on the development and characterization of a thermo-responsive ultrafiltration membrane. The membrane is made from a block copolymer called Polystyrene-block-Poly, diethyl acrylamide, PSB-PDEAAM. The PDEAAM block segment of the copolymer has a lower critical solution temperature, LCST, in water, similar to poly, N-isopropylacrylamide, PNIPAM, but with increased biocompatibility and without exhibiting hysteresis in its thermally induced switching behavior. The authors first synthesize the PSB-PDEAAM block copolymer using sequential, living, anionic polymerization protocols. The resulting copolymer is characterized using various techniques such as 1H-NMR spectroscopy, size exclusion chromatography, and differential scanning calorimetry. The morphology of the copolymer in the bulk state is investigated using transmission electron microscopy (TEM) and small-angle X-ray scattering (SAXS), revealing a hexagonal cylindrical morphology. The authors also study the micelle formation behavior of the PSB-PDEAAM copolymer in a binary mixture of tetrahydrofuran (THF) and dimethylformamide (DMF). They discuss the composition of the copolymer and solvent affinities in relation to the expected micellar structure and membrane formation. The PSB-PDEAAM copolymer membranes are fabricated using the non-solvent induced phase separation (NIPS) process. The membranes are characterized using scanning electron microscopy (SEM) and water permeation measurements at room temperature and 50 degrees Celsius. The results show a significant increase in water permeance, up to 23-fold, when the temperature crosses the LCST of the PDEAAM block segment in water. The authors conclude that the PSB-PDEAAM copolymer membranes exhibit thermo-responsive behavior due to the collapse of the PDEAAM chains above the LCST. They suggest that these membranes have potential applications in the biomedical field due to their biocompatibility and close LCST to human body temperature. The authors also mention the possibility of combining the thermo-responsive behavior with other external triggers to create additional switchable membrane features. The first figure in the paper shows the synthesis of the block copolymer PSB-PDEAAM. The synthesis is carried out via sequential anionic polymerization. The first step involves the polymerization of styrene in tetrahydrofuran (THF) at -78 degrees Celsius, followed by the addition of diphenyl ethylene to functionalize the active chain ends. In the second step, the diethyl acrylamide monomer is polymerized at 0 degrees Celsius using triethyl borane as a Lewis acid to control the polymerization. The resulting block copolymers are analyzed using size exclusion chromatography (SEC) and nuclear magnetic resonance (NMR) spectroscopy to determine their molecular weights and compositions. The molecular weights of the block copolymers range from 87.1 to 173 kg per mole, and the content of the PDEAAM block is found to be around 24 to 25 Wt%. This figure shows the bulk morphology of the block copolymers. The block copolymers are dissolved in chloroform and the resulting films are annealed at 130 degrees Celsius to induce microphase separation. Transmission electron microscopy (TEM) and small-angle X-ray scattering (SAXS) are used to analyze the morphology. For the block copolymers PS70BPDEAAM17 and COVALENTP1S131BPDEAAM42, a hexagonal cylindrical morphology is observed, with the PDEAAM block forming cylinders in a PS matrix. However, for the block copolymer PS125BPDEAAM43, only disordered structures are observed. The SAXS patterns confirm the presence of hexagonally packed cylinders in the first two block copolymers. This figure demonstrates the micellization behavior of the block copolymer PS125BPDEAAM43 in a binary mixture of tetrahydrofuran (THF) and dimethylformamide (DMF). The TEM image shows the formation of micelles with a diameter of 45 nanometers in this solvent mixture. This figure illustrates the proposed structure of the block copolymer membrane formed via the non-solvent-induced phase separation (NIPS) process. The membrane is composed of a polystyrene matrix with diethyl acrylamide (PDEAAM) lined pores. When the membrane is heated above the lower critical solution temperature, LCST, of PDEAAM, the collapsed PDEAAM chains create a larger pore volume and higher permeation. Scanning electron microscopy, SEM, images of the membranes fabricated from the block copolymers. The images reveal regions of good pore formation as well as regions with large areas without pores. These scanning electron microscopy, SEM, images show the surface and cross-section of the membranes fabricated from the block copolymers. The membrane of PS70BPDEAAM17 exhibits a porous structure with a sponge-like substructure. The membrane of PS125BPDEAAM43 has a similar structure, but with larger pore size. The membrane of PS131BPDEAAM42 shows a relatively dense surface with very large and ill-defined pores. This figure presents the water permeation measurements of the block copolymer membranes. The water permeation is determined at room temperature and at 50 degrees Celsius. The permeation at room temperature after exposure to 50 degrees Celsius is also measured. The results show a significant increase in water permeation at 50 degrees Celsius compared to room temperature for PS70BPDEAAM17, while the increase is smaller for COVALENTP1S125BPDEAAM43 and COVALENTP1S131BPDEAAM42. The permeation at room temperature after exposure to 50 degrees Celsius is either higher or lower depending on the specific block copolymer. Scanning electron microscopy, SEM. Images of the membrane surfaces before and after water permeation measurements at room temperature and 50 degrees Celsius. The images show changes in the surface structure of the membranes after exposure to elevated temperature, with some membranes exhibiting fewer pores or an irregular surface. This study presents the fabrication of thermo-responsive ultrafiltration membranes using a block copolymer composed of polystyrene and diethyl acrylamide, PDEAAM. The PDEAAM block has a lower critical solution temperature, LCST, in water, similar to N-isopropyl acrylamide, but with increased biocompatibility and without hysteresis in its thermally induced switching behavior. The block copolymer membranes were synthesized via non-solvent-induced phase separation (NIPS), and characterized using various techniques. The morphology of the membranes was investigated using transmission electron microscopy (TEM) and small-angle X-ray scattering (SAXS), revealing a hexagonal cylindrical structure. Water permeation measurements were performed at room temperature and at 50 degrees Celsius, showing a significant increase in permeance at 50 degrees Celsius due to the collapse of the PDEAAM chains. The membranes exhibited good reversibility and stability during the thermo-responsive switching. These thermo-responsive block copolymer membranes have potential applications in the field of biomedicinal separations. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.